Hello, welcome to my channel. Today we look at characteristic polynomial, eigenvalues, eigenvectors, and diagonalization of matrices. So these are very important topics, and I wish that you accompany me to the end. So I'll begin by characteristic polynomial, and then use that knowledge in the determination of the eigenvalues and eigenvectors. And then these three notions, the notion of the characteristic polynomial, eigenvalues, and eigenvectors will then be applied in the diagonalization of matrices. So they are very important topics, and I hope you learn a lot in the course of this video. So I begin by characteristic polynomial, and my definition is here. So this is an n by n matrix. If we are given an n by n matrix, then I say that the matrix A minus lambda I, where In here is the n by n identity matrix, and lambda is n scalar. It could be 1, could be 2, just n scalar. Then this matrix here is called the characteristic matrix. Now, if we get the determinant of this characteristic matrix, then this determinant will be called the characteristic polynomial. So characteristic polynomial is just the determinant of the characteristic matrix. As we proceed with this, to get the eigenvalues, we'll be equating this characteristic polynomial to 0, so that we solve for lambda here. So let's look at examples. And my first example is here. It says, given matrix A here, find the characteristic polynomial. So from our definition above, we want to get this matrix A and then subtract from it lambda I, where I here is a 2 by 2 identity matrix, which is 1, 0, 0, 1. A 2 by 2 identity matrix. And so that is the definition of the characteristic polynomial. So we get the determinant of this. And that's what I've written here. I've said that if I have this A, which is 5, 4, 3, 1, I should subtract from it lambda I. So lambda times this I will be lambda 0, 0, lambda. So when I do this subtraction, you find that 5 minus lambda, 5 minus lambda, then the 4 minus 0, which is 4, then 3 minus 0, which is 3, and 1 minus lambda here. And we're getting the determinant of this matrix. So that's what I've done here. And we all know how to get determinant of matrices. So it is this product minus this product. So this product is just 5 minus lambda multiplied by 1 minus lambda. Then minus this other product is 12. So 5 times 1 would be 5. 5 times lambda, negative lambda would be negative 5 lambda. And then negative lambda times 1 would be negative lambda. And negative lambda times negative lambda would be lambda square. Then there's a minus 12 here. So it's this that I just rearranged this to have lambda square. And negative 5 lambda minus lambda will be negative 6 lambda. And then 5 minus 12 will be negative 7. So this is the characteristic polynomial for this matrix. And that's how we do it. So I've said that note that the above characteristic polynomial can also be given by this. So what I mean here is that we can also reverse this order. You see, we've taken the determinant of a minus 5 lambda, no, minus lambda I, a minus lambda I, to get the characteristic polynomial. So what I'm saying in this statement is that you can also do it as the determinant of lambda I minus a and get the same result. That is what this statement means. So it's not a must that we must take a minus lambda. It can also be lambda I minus a, but you still get the same characteristic polynomial. So I want us to look at another question, another example. But before that, I wanted to give another way of getting the characteristic polynomial, which I feel is a bit simpler. And I've said that we can also compute the characteristic polynomial of a 2 by 2 matrix, and these are 2 by 2 matrix, by just taking lambda square minus lambda times the trace of A, plus the determinant of A. Now we all know that the trace of A is the sum of the elements along this diagonal. The sum of the elements along this diagonal. And then after that, you'll be getting the determinant of this matrix. So let's just use the above example to demonstrate this. So what I've said for is that we can also do it by just taking lambda square minus lambda times the trace of A, and then plus the determinant of A. Now, so the trace of A I've explained is the sum of the elements along this diagonal, so that is 6. So what I then have is lambda square minus 6 lambda. The trace of A is 6 times this lambda, here minus 6 lambda. Then the determinant of this matrix is 5 minus 12, this product minus this product. So it's 5 minus 12, which is negative 7. So you can see this is a very easy way of getting the characteristic polynomial. So if you know this method, it becomes very easy. For a 2 by 2 matrix, I've said it to be lambda square minus lambda times the trace of A plus the determinant of A. Now, so that means that I'll be using this formulas interchangeably. I can use this, or I can use the other one that I've already explained. So whichever one that I use, you should be able to follow. Now let's look at this example. So this example, I begin by using both methods so that you're familiar with both of them. The question is, given this matrix A, find the characteristic polynomial of this matrix A. But the other method the first one I said it would be the determinant of A minus lambda I, and this is them as 2, negative 4, 2, negative 3. Lambda I is lambda 0, 0 lambda. So when you subtract this, two, you have 2 minus lambda, and you have negative 4 minus 0, which is negative 4. You have 2 minus 0, which is 2, and you have negative 3 minus lambda. And then you get the determinant of this. It is this diagonal minus the product of this diagonal minus the product of this diagonal. So it is 2 minus lambda multiplied by negative 3 minus lambda, then minus the product of this diagonal, which is negative 8. So when you do this, you'd have 2 times 3, negative 3 would be negative 6. 2 times negative lambda would be negative 2 lambda. Then negative lambda times negative 3 would be positive 3 lambda. And then lambda negative times lambda negative will be positive lambda square. Then negative times negative will be positive 8. So you can just rearrange this to have lambda square. And this negative lambda, 2 lambda plus 3 lambda, that gives you lambda. And then negative 6 plus 8 will be 2. And that is how I found this. Alternatively, we can use the other formula that I've given to you. Let me just delete this. I've said it will be lambda square minus the trace of A plus the determinant of A. So that is lambda square, and the trace of A is this, the sum of these elements along this diagonal. That is 2 minus 3. That's what we see here, times lambda. Then plus the determinant of this matrix. So what you would then have would be, at this point I have negative lambda times this negative becomes positive lambda. And then this one gives you positive 2. So that is the other way you can do it. Let's look at another example. So the example is here. Find the characteristic polynomial for this matrix. Is the same. We do it the same way that we take matrix A minus lambda I and get the determinant. Or you can also take lambda I minus A and get the determinant. So whichever way that you want to use, it will still give you the same result. It's simply the characteristic polynomial. Now, so I used this A minus lambda I and found the determinant of that. So it's the same as subtracting lambda from the leading diagonal. So it will be 2 minus lambda. The rest in this row remain the same. So I only subtract along this diagonal. So this will be 2 minus lambda. This will be negative 3 minus lambda. And this will be 2 minus lambda. And the rest remain the same. So that's what you see here. And then I find the determinant of this matrix. We now have to get the determinant of a 3 by 3 matrix. But if you don't mind, I can remind you that I take these elements, 2 minus lambda, and then multiplied by the determinant of the matrix that remains when I delete this row 1 and this column 1. When I delete the row of this element and the column of this element, I'm left with the negative 3, negative lambda, negative 3, negative lambda, 3, 2, 2 minus lambda. Then I will say minus times this element. That element is negative 4. And then multiply that by the determinant of the matrix that remains when you delete the row of 4 and the column of 4. So when you delete the row of 4 and the column of 4, you're left with the 2, 5 and 3, 2 minus lambda. And then plus, I'm now at this. I'm expanding this along the first row. So when you delete the row of 1 and the column of 1, you're left with the 2, negative 3, negative lambda, then 5, and a 2. So you just simplify this now. This is a determinant, and that is also a determinant. But this determinant times this. Let me put this one inside a bracket. Yes, this is determinant times this. Then this positive 4 times this determinant. And this 1 times this determinant. And this one is what I wrote here. So when you simplify, and you know how to simplify that, you will get this as the characteristic polynomial. So this is the characteristic polynomial of this matrix. Now, just as I said earlier, we could have another method, and I had already said it will be lambda I minus A. So if you do this, what you will get will be, it is the same as multiplying the whole of this by negative. will give you an answer that is negative of this. So it will give you positive lambda cubed minus lambda square minus 11 lambda plus 49. So for a 3 by 3 matrix, that is what you get. It will give you negative of this. This does not happen for a 2 by 2 matrix. For a 2 by 2 matrix, you remain the same answer that you found earlier. But both of these are the characteristic polynomial. So this is a characteristic polynomial, and this is also another characteristic polynomial. So, but it's the same thing. The same thing. So when you find this, you should not struggle to find this. It is the same thing. Now, so finding the characteristic polynomial for a 3 by 3 matrix, and I've written it here, and I've said, not that I've already explained, but now the method I want to explain is this. Is that you'd have a trace, lambda cubed minus lambda square multiplied by the trace of A plus lambda multiplied 3. Then what you need to know, what are these C11, C22? So C11 is the cofactor of element A1. And C22 is the cofactor of element A22. And C33 is the cofactor of element A33. That means we're getting the cofactor of the elements along the leading diagonal and then adding those cofactors and multiply by lambda. Now, if you don't know how to get cofactors, I'll be showing you how to do that. Then minus the determinant of A. So I want to use the following example, just the same example above, but I will do it here using this method. So the question is, we will do the above example using so I said that if you do not know how to get the cofactors, and you're getting cofactors of these elements, this element A11 and this element A22, and then this one is the element A33. So how do you get the cofactor of this element? The cofactor of this element, or you delete the row of this element and then the column of this element. So the cofactor, therefore, is the determinant of the matrix that remains after that deletion. So when I delete element A11, this is the element, and delete the row of that element and then the column of that element, I'm left with the negative 3, 3, 2, 2. So the determinant of that is the cofactor C1. And you can see that is negative 6 minus 6, which is negative 5. Then I come to this other element and get its cofactor. So I delete the column of this element and the row of this element. I'm left with 2, 5, 1, 3. So 2, 5, 1, 3. So this determinant is the cofactor C22. Then I come to the last element here. Delete its column and its row, and you can see the matrix that is left. So the determinant of that matrix is the cofactor C33. So it's very easy. So you just get the cofactor of this element, cofactor of this element, cofactor of this element. And then after that, you now come to finding the determinant of matrix A, which you are aware of. You know how to get a determinant of a 3 by 3 matrix. But if you do not know, again, it's 2 times the determinant of the matrix that remains when I delete the row of 2 and the column of 2. So that is negative 3, 3, 2, 2. Then minus, that means I have to delete the whole thing. So then minus this, minus negative 4 times the determinant of the matrix that remains when delete the column of 4 and delete the row of 4, and that will be 2, 5, 3, 2. Then plus the determinant, I'm here, I'm doing it along the first row. So when I delete the column of 1 and the row of 1, I'm left with this matrix. I'm left with the 2, negative 3, 5, 2. So when you do that, then you'll be having the determinant of matrix A. But of course, there are so many ways of finding the determinant of a matrix. If you do not know, then you can check in one of our previous videos on how to get determinant of a higher order matrices. Now, so we now have the cofactor C11, cofactor C12, and cofactor C11, cofactor C22, and cofactor C33, and the determinant of the matrix as negative 49. So what then follows is to get the characteristic polynomial. And our formula says that that characteristic polynomial will then be given by lambda cubed minus lambda square times the trace of A plus lambda times the sum of the cofactors or the leading diagonals, and then minus the determinant of A. So the trace, again, we know how to get it, is the sum of the elements along the leading diagonal. So the trace will then be 2 plus negative 3 plus 2, and that is positive 1. That's what you can see. I've written it here. That's what I've written here. 2 plus negative 3 plus 2, that is the trace. Then the sum of the cofactors. The first cofactor was negative 12, the other one was negative 1, and the other one was positive 2. And these ones are here. And then minus the determinant, which is negative 49. And when you simplify this, you get the characteristic polynomial as this. I think you are now familiar with how to get characteristic polynomial, and you have those two methods. They're very easy, but let me look at another example to make it very clear. Okay, look at this example. Example says, find the characteristic polynomial, please. Now, so I want to use the other method. I said you can have lambda I minus A, so that is the one I want to use this time, because we've been using A minus lambda I. But I want to interchange and see that we get the same thing. So if I subtract this, the whole of this from lambda I. This is lambda I. This is our lambda I. This is our lambda I. Lambda times I, where I is the identity matrix. We are talking about a 3 by 3 matrix, so I will also be a 3 by 3 identity matrix. So I then subtract 1, 0, 1, 1, negative 3, 0, and then 2, 2, negative 3. So when you do that, it will be lambda minus 1. That is what you see there. Then it will be 0 minus 0, and then 0 minus 1, it will be negative 1, and then 0 minus 1, it will be negative 1. So you do the whole thing, you do this subtraction, and that's what you get. And after subtracting that, now get the determinant of this matrix. Get the determinant of this matrix. And again, I repeat for those who do not know how to get the determinant, it will be this element times the matrix, the determinant of the matrix that remains when you delete the row and the column of this element. When you delete the row and the column of this element, lambda minus 1, we are left with this. So the determinant of that. Then next, it will be negative 0. Then you delete the column of 0 and the row of 0. So it is negative 0 times the determinant of the matrix that remains when you delete that row and this column. So it is negative 1, negative 2, 0, lambda plus 3. But you know that this result, of course, will be 0, because anything multiplied by 0, we get 0. Then it will be plus negative 1. Then delete the row of this one and the column of this one, and you're left with the negative 1, lambda plus 3, negative 2, negative 2. Now, so this means the determinant. Find this determinant and multiply by this. So when you find this determinant, I found it to be this lambda square plus 6 lambda minus plus 9. And let me do it maybe for those who have problems with it. So it is just lambda plus 3 and then lambda plus 3. So this product along this diagonal, then minus this other product, but this is 0. So when you multiply lambda times lambda, you have lambda square. Lambda times 3, you have 3 lambda. And then 3 times lambda, you have 3 lambda. And then 3 times 3, you have 9. So simplify this. This gives you 6 lambda. That's what you see. There's a lambda square. And then there's a 9. And then this one gives you 0. So you're here. Negative 1 into this product gives you positive 2. And this other product gives you negative 2 lambda and negative 6. So subtract this from 2. And when you open this bracket, this is what you get. This is what you get. So when you simplify that, you have the characteristic polynomial. So let me clear this, and then we'll look at. You may want to try the other method. I've tried it here. I've done it here. So just do yours and then confirm. Why are you getting the cofactor C11, cofactor C22, factor C33, and then remember the determinants and then the trace. So it's lambda cubed minus lambda multiplied by the sum of the cofactors and the minus determinant of n. So you try at your own time and see that you get the same answer. And then it's yourself that will tell which of the two methods are similar. Let us now look at eigenvalues and eigenvectors. So we begin by defining what eigenvalues are. And I say that let A be an n by n matrix of a field K. Then a scalar lambda in K will be called an eigenvalue of A if there exists an non-zero column vector. If there exists this column vector X, such that the product of A times X will be the same as will equal to lambda times X. So this non-zero vector, which we write as a column vector, is what we call the Eigenvector of A corresponding to lambda. So what I mean is that for lambda in K to be an eigenvalue of matrix A, there must be a vector which we write in column form and call it Eigenvector X corresponding to this lambda, such that matrix A times this eigenvector will give you lambda, and lambda is the eigenvalue times the eigenvector. That this product should be, fulfilled for lambda here to be an eigenvalue of A and X here to be its corresponding eigenvector. Now, so that is what we'll be doing in most of our formula, in most of our examples, to verify that a certain lambda is an eigenvalue of a matrix A, and also to verify that a certain X is an eigenvector. So we'll be using this expression here to verify that. Now, so sometimes instead of using the word eigenvalue and eigenvector, we use the terms characteristic value and characteristic vector. So characteristic value would mean eigenvalue, and characteristic vector would mean eigenvector. We can also use the words proper value and proper vector respectively when referring to eigenvalues and eigenvectors. Now, what I've written here, and is very important, that these eigenvectors corresponding to different eigenvalues will be linearly independent. Just explain that. Let us look at the example. And the example says, consider this matrix A and show that this vector here, 2, 1, is an eigenvector equals to 4. So this is the eigen value. So I want to show that this positive 4 is an eigenvector is this. And then we'll proceed with this example B here and says, show that this negative 1, 1 is also an eigenvector, is the eigenvalue of this matrix. Now look at how slightly I've expressed this one differently. You know what this means? This is a transpose. So the transpose, you know, and you've learned that before. So when I write this, transpose is the same as this vector here. So this to mean the same thing. This is the transpose. If you're given a matrix and then the transpose is the matrix, to get the transpose, you would write the rows as columns in the order in which they're here. The first row, you write the first column. Second row, write your second column. So this, or columns as rows. The first column, write it as first row. That's what I did here. So this column, write it as a row, and this is the transpose. Now, so let's go back to the question. The question is, show that 4 is an eigen value of A and its corresponding eigenvector is B. So we just use the definition above. We say that we would have that matrix A times the eigenvector should give us eigenvalue times the eigenvector. So this is a matrix A. So let's see. 2, 3, 1, 2. Multiply it by the eigenvector here and see what you get. 2, 1. So when I multiply, it is 3 times that, which is 6, plus 2 times this, and that gives me 8. And then 1 times 2 will be 2, plus 2 times 1, and that gives me what? That will be 2 plus 2, that gives me 4. And I can see that this is the same as 4 multiplied by 2, 1. This is the same as 4 multiplied by 2, 1, which is the same as 4x. This is the same as 4x. 4x is the vector. And this was the same as ax. So ax is A times x. It has given me 4, 8, 4. You know how to multiply these vectors. And when I look at it, I can factorize 4 outside and I would have 2, 1. And this is just 4 times the vector. So the vector was this, vector x. So that means, therefore, that this is true. That it's true that 2, 1 is an eigenvector of A corresponding to eigenvalue 4. What about this one? Let's see. I have A. So I want to call this one x. So A times x then will be 3, 2, 1, 2. And our x is negative 1, 1. Our x is negative 1, 1. So when I multiply this, I would have negative 3 plus 2, which is negative 1. And then I would have negative 1 plus 2, which is 1. And this is just the same as 1 multiplied by negative 1, 1. Which is same as 1x. Is same as 1x. That means that it is true that this negative 1, 1 is an eigenvector of A corresponding to lambda equals to 1. So that is how we will do that. I want to show you my earlier working for the sake of those who are writing notes. I want to show my earlier working, and here it is. I've just explained the use of the transpose, that we can use the transpose if we do not want to write in column form, then we can use the transpose. So like the earlier one, the vector was 2, 1. So if you don't want to write it as this, you can write it as 2, 1 transpose. It's the same thing. So that is what I've just written. And I've said that these two vectors, since they belong to two different eigenvalues, these two therefore are linearly independent. They are linearly independent. And you know what linear dependence and linear independence mean. Let's look at this other example. The example says, let me just come back to what the example is. The example is here. It says, let A be this matrix, and then I have this vector here, mu, and the vector v here. The question is, are mu and v eigenvectors? If yes, find their respective eigenvalues. Now, to do this, I would use the earlier knowledge that if I have A times the vector, I will get lambda times the vector. The matrix times the eigenvector should give me eigenvalue times the eigenvector. So I'll just do that for this matrix. Let me just do that. So what is A mu? A mu is 2, 2, 1, 3, followed by negative 2, 1. And when I do that, I would have negative 4 plus 2, which is negative 2. I'm just multiplying. 2 times negative 2 will be negative 4. And 2 times 1 will be 2. When I add those two, I have negative 2. Then negative 2 plus 3 will give me 1. And this can be written as 1, negative 2, 1. I'm just factoring the eigen vector outside here. And what I notice is that this is the same as 1x, 1 mu. The same as 1 mu. So what this means to me is that yes, mu here is an eigenvector corresponding to lambda is equals to 1 as an eigenvalue. So the eigenvalue for this vector is lambda 1 is just 1. Let me check if the other one is also an eigenvector corresponding to any eigenvalue in A. So I take A times B. A times B will be 2, 2, 1, 3. Then multiply by 1, 1. That is my V. And when I do this, I will have 2 plus 2, which will be 4. And this one will be 1 plus 3, which will also be 4. And this one can be written as 4 into 1, 1, which is 4b. So that means AB is equals to 4b. In other words, this vector here, yes, it is an eigenvector of matrix A, and it corresponds to eigenvalue 4. The question was find their respective eigenvalues. So for this one, the eigenvalue is 4. And for this one, the eigenvalue was 1. So I can show you my earlier work here so that you can arrive. So this is my earlier working for the solution. Now, another example, I want you to understand this notion of eigenvalues and eigenvectors before we even go into calculating. So the question here, show that this is an eigenvalue of this and find the corresponding eigen, or show that it's an eigenvector and find the corresponding eigenvalue. So the same reasoning as above, just multiply this and this. When you multiply these two, you get 8, 12. And we can think of how to factorize this one. And you can see it has been factorized. In fact, this is the same as 4 the same as 4. So that means that mu here is an eigenvector. And the corresponding eigenvalue is 4. And that's what I've written. So I have not included the eigenvalue. So the eigenvalue, therefore, eigenvalue is 4. That completes the result because the question was find the corresponding eigenvalue. So it is 4. Okay, so let's look at this other example so that this notion becomes clear to us. And the example here is, let there be this matrix, and I have this vector and this other vector. And the question is, are these vectors eigenvectors? Are they eigenvectors of this matrix? So the reason is the same as above. Multiply each of these vectors with the matrix. So I began with the mu, matrix A times mu. I found this, and towards the end I discovered that I could factorize it. So I have 4 mu. So this first one means, therefore, that mu here is an eigenvector, and the corresponding eigenvalue is 4. But let's check for this one. When I check matrix A, then I think of how can I factor, and I discovered that there's no number which I can multiply by 1 and negative 1 to get this. There's no number which I can multiply by 1 to get 3, and the same number multiplied by negative 1 to get negative 5. There is no such number. So that means there is no eigenvalue for this vector. So that therefore means that this vector is not an eigenvector for this matrix. Now, so that means that those kind of questions are now easy for you. In fact, you can do this. You can do this one. I've already done it, but you can do it, and then you may want to compare your result with mine. So my result is here. This one. This one is slightly different. This one is slightly different, but we use the same knowledge. The question is, show that negative 3 is an eigenvalue of matrix A, and then find the corresponding eigenvector or eigenvector. So we use the same knowledge. That we used, for example, in the definition, we say that lambda, let me call it lambda, that ax should be equal to lambda x if lambda is to be an eigenvalue and x be its corresponding eigenvector. So when you take this product to the left, what you would then have would be ax minus lambda x is equal to 0. Or that I can factor x out and have a minus lambda divided by x is equal to 0. But whenever I have lambda, let me multiply by r. Because lambda is just a scalar, so for it to be a matrix, I have to multiply by r. So that I have a minus lambda I multiplied by the eigenvector to give me 0. So that's what I want to do. That's what I want to do. So I've said let x, the eigenvector, be x1, x2. So this is the eigenvector corresponding to this lambda equals to 3. So instead of this lambda, I have 3. This one you see. So that you see I had this. So when I write it here, I have a minus 3I multiplied by x is equals to 0. But this minus and this minus gives me positive. That's why you see this. Now, so let me just do it now. Let me just do it. In fact, this statement, you may want to include it. You may want to include. I did only this part. But if you want to do the whole part together, as we will see in the other examples, you want to do all the parts together. But I've only chosen to do this part. When I do this part, I have a, which is here. So it is a. Then to that a, I'm adding 3I, which is 3, 0, 0, 3. So that's what you see, a plus 3I. When you do that, you get this. So I just looked at the columns here. I just looked at the columns and discovered that these columns were linearly dependent. And since they're linearly dependent, it means that this, if you were to do this, would get a solution or infinitely many solutions. So we get either a unique solution or infinitely many solutions. So if that happens, if there is a case where you get solutions, then it means that 3, this lambda is equals to -3 is an eigenvalue. But if you have no solutions, then it's not an eigenvalue. So that therefore means that up to there we've answered the first part of the question. The first part of the question was show that -3 is an eigenvalue. So we've answered it. Say that thus -3 is an eigenvalue of matrix. And how do I conclude this? By looking at this, the columns here are linearly dependent. You know what we mean by linearly dependent? If you have vectors which are linearly dependent now, then we mean that we can find the scalars x, y such that the first scalar times the first vector plus the second scalar times the second vector would give you 0, 0, and that these scalars exist and not all of them are 0. They exist and not all of them are 0. Or that the other definition of linear dependence is that this determinant would be 0. So the determinant here is 0. Look at this. 6 minus 6. 6 minus 6. So the determinant is 0. So if the determinant of the matrix form is 0, then that it means that those columns are linearly dependent. It means the columns are linearly dependent. So we look at that. But what we wanted to show was that -3 is an eigenvector, and that is what we've shown. Now, so the interesting question here is find the corresponding eigenvectors. Find the corresponding eigenvectors, and with that we will use this. We will solve this equation because we want to find this x. So we solve this equation. Let me show you what I did. So I've said here that to find corresponding eigenvectors, we solve this. And when you, this is just this. I took a plus 3i, I was given as 6 to 31. So when you multiply by x, and I've selected this x be x1, x2. So when you multiply and equal to 0, this is what you come up. Now, so we can now use Gaussian elimination to find the value of x1. You don't even need to come up with this point. From just here, from this, you can straight away come to Gaussian elimination as I've done it here. So you can see what I want is to make this value here positive 1. I want to make it 1, but it's not always a must, it must be 1. I can even leave it the way it is. But what is most important is that this one must be 0. So I think of how do I make this one 0. But in this example, I divided this by 6, this row by 6, row 1 by 6. I divided row 1 by 6, and doing that, this is my row 1, and the row 2 I left it the way it is. Then I use this element here to create a 0 in this position. So that meant that I multiply row 1 by 3 and subtract from row 2. Multiply row 1 by 3 and subtract from row 2. So 1 by 3 will be 3, subtract from 3, over 0. Then a third times 3 will be 1. Subtract that 1 from this one, over 0. So this is what I'm left with. I'm left with 1 plus a third. In fact, it's a 1 x1. A third x2 is equal to 0. I want to get the value of x1 and x2. Looking at this equation, I discovered that x2 is a free variable. Since x2 is a free variable, I'm allowed to equate it to any parameter. So I can say let x2 be t. I am allowed to equate it to any parameter. So if x2 is t, then what does x1 become? x1 becomes negative a third of x2, but x2 is t. So x1 is negative a third t, while x2 is t. Now, this t is the any parameter, and one might want to make it 1. You want to say let t be 1, or let t be 2, or let t be 3. So if t is 3, then what would be x1? x1 would be negative 1. So that's what I've explained. So this equation of x1 plus a third x2 is equal to 0, or that x1 is negative a third x2. So if x2 is actually a third s, so what is my x? My x was x1, x, or I may want to factor s out and then have this. Remember that it can be 1, can be 2, can be 3, and so on, but not 0. So what is the eigenvector? That was the question. So the eigenvector corresponding to lambda is negative 3. I've said would be this. Would be negative a third 1, or its multiple. Any multiple 1, it remains negative a third 1. If there is 2 out of 3, 2. If s is 3, it becomes negative a third, no, negative 1, 3. So just multiply by that. So that's it. Or 1, 3. By realizing fraction, and the denominator is 3. So I multiply each of these elements by the denominator. This is denominator 3. Multiply the first element by 3, get negative 1. Multiply the second element by 3, get 3. So the eigenvector is this, or multiples of this. But we will look at more other examples on how to determine eigenvectors and eigenvalues. Now, so what I've written is just what I've been explaining, so you can read it later. I want to define the eigenspace. I want to define eigenspace. And my definition here says let A be an n by n matrix and lambda is eigenvalue. Then the set of vectors corresponding to lambda together with the 0 vector will be called the eigenspace of lambda, and we shall denote it by E lambda. So that from the previous example, where we got what did we find as the eigenvector? The previous example, this was the eigenvector for this, and multiples of this. In fact, this is what we have written, and this is what I have written S into this. So the set of all this, and you know when I talk about the set, the kind of brackets I'm using. So the set of this, this set is what we call eigenspace. That set is the eigenspace. So it's the eigenspace of eigenvector -3. So that's how we denote. That's what I'm saying. We should write as P number. Of this matrix and find the basis is also very important. Let's know what it is. We shall know it through this example. So I want to do the example here. What is the question? Show that it choose an eigenvalue of n. This is our n. So we use the same knowledge. We know that we will have to take matrix A minus 2i and the multiply by zx and equal to 0. But then we shall look at to see whether this part here gives us linearly dependent vectors, the column of this part. So that's what I said. Let x be this, be an eigenvector corresponding lambda is equals to 2. So what is A minus 2i? A minus 2i is this. It gives us 1, -4, 2, -8. Let's look at this determinant of this matrix. It is -8 plus 8, and that gives us 0. So the determinant is 0. That means these columns are linearly dependent. So I've written the columns of A minus 2i are linearly dependent. And what that therefore means is that this equation has solutions. And so therefore, that means that 2 is an eigenvalue of matrix X. 2 is an eigenvalue of matrix X. Now that one is very easy. So what is in fact very important is to find the eigenvector and then the eigenspace. That's what the question wants us to find. The basis of the eigenspace. That means proceed and find the eigenvalue first, and then write it as a set. So to proceed and find the eigenvalues is this ax minus 2x equal to 0. So you have x1 minus that. So solve this by Gaussian elimination. This is already 1. So use it to create a 0 in this position, multiply row 1 by 2, and subtract your result from row 2. So 1 times 2 from 2 will be 0, and then -4 times 2 will be -8. Negative from -8 we get it. So what we then get? What we then get is x1 minus 4x2 is equals to 0. So again, 4 here is a free variable, call it S. So I would then have x2 here. x2 is a free variable, call it S. So that then means that x1 will be 4x2, but x2 is S. So that the eigenvalue will be 4s and s, x1, x2. Or if you want, you can write as 4, 1, then you put s outside. So that means the eigenvalue is 4, 1, or the multiple of 4, 1. Multiple of 4. So the multiple, that means because S here is a parameter, so it can be 1, it can be 2, it can be 3, but it should be 0, and so on. So eigenvectors, eigenvalues can be 0, but eigenvectors should not be 0. Now, what is the question? The question is, find the basis of the eigenspace. So you know the eigenspace is this. Eigenspace is the eigenspace. So the set of all the eigenvectors. The set of all the eigenvectors is the eigenspace. But a basis will be this set. The set comprising of 4. The set comprising of 4 is the basis. So let me just show you my earlier working so that you have clear what we said you. And this is what I've written. I've said that the eigenspace corresponding to lambda is equals to 2 with this. And we can also write it as by transpose. But the basis of this eigenspace of this, which you can also write as a transpose. So you need to know how to express your eigenspace and basis. And another very important term is the null space. The null space. The null of this. So again, I'll show an example so that you understand what the null space is. Look at this question here. Show the eigenvalue and find the basis. I'll just show you my results, but you now have the way you should work it. So just look at my result, compare your result and mine. And what I'm interested in is the basis. How to write the basis. That's what I'm interested in. Okay. Let's look at this other example. I'm sure that the previous one you've seen it, and that you can look at it clearly and compare the result with yours. But I want us to look at the next one here. It says, show that lambda is equals to 1 is an eigenvalue for this matrix and find the basis for its eigenspace. Again, it's just the same thing actually, same working, and I've done it. 2 steps. The only thing I've changed the dimension of the matrix. The size of the matrix is what I've changed, but the rest, the work. Now let us begin from here. Let's begin from here. The question is, find the eigenvalues and the corresponding eigenvectors of this matrix. So I will continue from here. Remember, we say that we first of all get the characteristic polynomial of this lambda I. To get, this is the determinant of this is the characteristic polynomial. And then after getting the characteristic polynomial, we would equate it to 0. So we'll be finding the determinant of a minus lambda I, and equate this to 0. Solve this to find lambda, the value of lambda. So those values of lambda are what we call the eigenvalues. Then once we are there, then again I'll explain to you how to get the eigenvectors from there. Let's first of all do this. Find the characteristic polynomial and equate it to 0, and then solve for lambda. And that's what I've just written. Now, so we already said that the other formula will be lambda square. For getting the characteristic polynomial, lambda square minus lambda multiplied by the trace of a, and then plus the determinant. Right now, you are familiar with how to get the characteristic polynomial because we began with that. So it will be lambda square minus the trace of a is just 5 plus 1, which is 6 lambda here, And then the determinant of this matrix is 5 minus 12, which is -7. This is the characteristic polynomial. Now equate this to 0, and this quadratic equation, you can solve it by either factorization or by quadratic formula. So I did solve it by factorization to get lambda is equal to 1, lambda is equal to 7. Also, you have to factorize this thing. So this is what we get. Lambda is equal to -1, lambda is equal to 7. So these two are the eigenvalues for this matrix. Now, after you found the eigenvalues, okay, could there be somebody who does a lot of factorize this? Let me just do it. You look for two values whose product is -7 lambda, -7 lambda square, and the sum is -6 lambda. And so you would find that the product of two numbers that will give you is -7 lambda and lambda. So that the product will give you -7 lambda square, and the sum would give you -6 lambda. And so what you would then write is lambda square. Instead of this, write those two terms, -7 lambda plus lambda minus 7 is equal to 0. Now you can factorize this and end up to, so lambda is common, put it outside, you have lambda minus 7, then plus 1, and again 1 is common between these two, you have lambda minus 7 and equal to 0. So then it will be lambda plus 1 multiplied by lambda minus 7 is equal to 0. So at this point, equate this first term here, lambda plus 1 to 0, to get lambda 1 plus -1. And also equate the second term, which is lambda minus 7 to 0, to get lambda 2 as 7. These are the characteristic of the eigenvalues. What are the eigenvalues? Now, so you now have the eigenvalues, you need to get the eigenvectors corresponding to each of the eigenvalues. So I begin by finding the eigenvector corresponding to my first eigenvalue. And I know that to do that, I need to solve this equation. To do that, I need to solve that equation. I just say let x1 be x, be x1, x2. And this equation here, this equation, this is a plus. It's plus because of this negative. It was supposed to be negative lambda I, but lambda is -1. So it becomes plus. So this is what I have. A minus lambda I. And this will give me 5 minus -1, which is 6. 4 minus 0, which is 4. 3 minus 0, which is 3. And 1 minus -1, which is 2. Then multiply this eigenvector here. Then what we need is to equate it to 0 and solve. We need to equate it to 0 and then solve. So let me show you what I did after that. What is that? S6 here. So I said we need to equate it to 0 and then solve. So that's what I just did here. Equate to 0. So when you equate to 0 and multiply these matrices, this is what you arrive at. And then use Gaussian elimination. 6, 4, 3, 2. We already had done this. So you remember we divided this equation 1, 0, 1 by 6. When you divide row 1 by 6, this is what we get. I maintain row 2. And then use this row 1 to create a 0. That means I need to multiply row 1 by 3 and subtract from row 2. When you do that, and you know how to solve system of equation by Gaussian elimination, and even several other methods, so you can solve this is still the equation. Now, so when you reach here, you realize that x2 is a free variable. X2 is a free variable, and therefore we let it be a parameter t. So if x2 is t, then from this equation, x1 would be negative 2 out of 3t. So the eigenspace, we said we can write it, is the set of all the eigenvectors corresponding to a given eigenvalue. So it is the set of this. This is the these are the eigenvectors. These are all the eigenvectors, which you can also factor like this. But remember at this point, I said you can even multiply this one by 3 and multiply this one by 3, because 3 is the denominator. So you can multiply it by this first element and multiply this first element, this second element, and it gets negative 2, 1. You can do that, although I did not do that in this question, but you can still do it. So the eigenvector corresponding to this eigenvalue is this, or any other non-zero model of this. Now we use the same reasoning to get eigenvectors corresponding to lambda 27. So just let x be x1, x2. So you need to get a minus 7i multiplied by this x and equate to 0. So first of all, I did a minus 7i, that's a minus 7i multiplied by x, and that gives this. So then I did equate that to 0. So when I equate to 0 and multiply these two matrices, I come up with these two equations. And then solve these two by Gaussian elimination. That's what I did here. I arranged the first equation here, and then the second equation here, and the zeros. And then I decided to make this first entry here positive 1. It's not a must that you must always do that. You can leave it as the negative 2. But what is important is that the element here should be 0. The element below this element should be 0. All the elements below this element should be 0. So when I decided to make it 1, I divided the entire row by negative 2 to get this, and then maintained the second row. And I decided to use this 1 to get the 0 here. So I multiplied the entire row by 3 and subtracted the result from 2. So 1 times 3, the answer you get, subtract from 3, and you will have 0, 0, 0. At this point, you notice that x2 is a free variable. X2 is a free variable, so we make it the parameter t. And so if x2 is t, from this equation, I can say that x1 would be 2x2, but x2 is t. So x1 therefore is 2t. The question wants us to get eigenspace corresponding to the eigenvalues. So it is the set of all the eigenvectors, and we call that eigenvector x1, x2, and we found that the value of x1 would be 2t, and the value of x2 would be t, or we can factor t out and have this. So this is the eigenspace. What about the eigenvector? Eigenvector could be this 2, 1, or any other multiple of that. Any other multiple of that. So we now look at an example involving a 3 by 3 matrix and even higher order matrices. The question is find the eigenvalues and the corresponding eigenspaces. To get the eigenvalues, we subtract lambda I from this matrix. And it's the same as subtracting lambda from this given diagonal, and then getting the determinant of the matrix, so that you have the characteristic polynomial and equate the characteristic polynomial to 0. So we know how to get characteristic polynomial using various methods. This is one of the methods I taught you, where we are getting the cofactors C11, C22, and so on. So this is another method of finding the characteristic polynomial. But what is very important is that after finding the characteristic polynomial as it is here, equate to 0 and solve for lambda. So when you equate lambda cubed minus 7 lambda to 0, you can factorize lambda, where you have lambda square minus equals to 0, or outside the bracket equals to 0. So lambda outside the bracket equals to 0. So you can call it the first eigenvalue. And this other one is lambda square minus 1 equals to 0. So when I take one the other side, you have lambda square equals to 1, or you can get square root and find that lambda is equals to plus or minus 1. So those are the eigenvalues. So the eigenvalues therefore are lambda 1 is equals to 1, lambda 2 is equals to -1, and lambda 3 is equals to 0. There's no order. You can, any of them can be lambda 1, and any of them can be lambda 2, and so on. There's no order. Just getting the values of that, the values of lambda. So these are the eigenvalues. So we now want to get eigenvectors corresponding to each of these eigenvalues. So I say let X be x1, x2, x3, because we are dealing with 3 by 3 matrix. So then you know that what I need to do is get matrix A minus lambda I multiplied by x and equal to 0. I need to do lambda A minus lambda I multiplied by x and equal to 0, and see whether I can find the value of x, because we already know what lambda is. So because if I'm getting for this, I already know that lambda is 1. So the only unknown here is x, the one I want to find. So this is A minus lambda I, but lambda in this case is 1. Lambda I multiplied by x. So when we do this first bracket, this is what we get, multiplied by this x. Now you don't need to multiply them out. It's a waste of time. Just know that for me, use row reduction or Gaussian elimination. Let's use Gaussian elimination. Just arrange this here straight away, and you can see that I've already arranged them here. The only thing I've done is that I've interchanged these two rows. I've interchanged these two rows because the first element here must be non-zero, because I can see those below it are non-zero. So this must be non-zero so that I use it to create zeros below it. So then I choose to take this one up, and this one comes down. I would have taken this one up and this one to replace it. But I chose to interchange row 1 and row 2. So this is what I did. And then I use now this element here to create zeros below it. There's already a 0 here. So I only need to create a 0. So how did I create a 0 there? I took row 2, row 3, minus 3 row 1. No, minus 2 row. Because this side. So this times 2 from this I have here. This times 2 I have -6. From -3 I have 3. And this times 2 is 2. From this I have -2. Then next, I want to use this to create a 0. So what you notice is that I just want to take row 3, then plus row 2. Then I have a 0 in this position. So that's what I did, and I have this. So at this point, you notice that I have x1 minus x2 plus x3 is 0, and this one is 0x1 negative 3x2 plus x2x3 is 0. So these are the equations that I get from this matrix. Now I can see that x1 is a leading variable, x2 is a leading variable, but x3 is not a leading variable. So therefore it's a free variable. Let it be t. Let it be t. X3 is a free variable. Let it be t. So if x3 is t, taking the other side of the equation 2, so you then find that if you make x2 a subject of the formula, this is what you have. Negative 3x2 is equals to negative 2x3. But x3 is t, so that means x2 is negative 2t divided by negative 3. Or x2 is 2 out of 3 t, the negative constant. So that's why you see this answer. That's why you see this. And then what about x1? So you just come to this other equation where x1 is supposed to be negative. It's positive 3 x2 minus x3. But we know what x2 is. We know what x2 is. And we know what x3 is. We know what x3 is. So when you substitute them, you substitute x2 here, you will find 2t. And this one is t. So when you subtract, you find the t. That's why I wrote and said that x1 would be t. Now, so what is the eigenvalue? x1, x2, x3, that is x1, is t. x2 is 2 out of 3 t. And x3 is t. But you can also factor t out to have 1, 2 out of 3, 1. This is 2 out of 3, and this 1 t outside. You can also want to remove this fraction by multiplying this by 3, the entire thing by 3, and then when you do that, you get 3, 2, 3. And that's what you see. That's what you see. So the question is, the eigenspace, therefore, I want you to see the eigenspace and the null space. The eigenspace is the set of all the eigenvectors, and the null space is the null space is, in fact, is the same as the basis. It's the same as the basis. So you now know what the null space is, and that is the only thing that was left for me to show you. I've shown what eigenspace is, what the base. The eigenvector for the last lambda 1, lambda 2 was this, and the procedure will be the same. That I need to get a plus I, because this is supposed to be what? Supposed to be a minus lambda I. But I is negative, lambda is negative 1. So this is a minus 1 I. X equals to 0. I times 1 is just I, and negative times negative positive. That is 1 plus I x is equals to 0. That's how you see I've written a plus I. So this is I, and this is a. So when you add this get and you multiply by x, so from here you come straight to Gaussian elimination and apply it. You know how to use Gaussian elimination. So I only look at the last part of this. Of course, this gives me this. And from here, I can see that x1 is a leading variable, x2 be a leading variable, but x3 is not. So I make x3 be 1, be t. I make x3 be t, because it's a free variable. But this last equation, this one, it tells me that x2, negative x2 is 0, or x2 is just 0. And this other one tells me, you see, this is 0, because it's x2, because it will be 1, it will be x1 minus x2 plus x3 is 0. But we've already found that x2 is 0. So, and we've already said let t, x3 be t. That means that x1 will be negative t. X1 will be negative t there. And then from there, we can straight away write the matrix. We can straight away write the vector. Now, this is what I get. So this is an explanation of what I've already explained. Already explained that x3 will be t, x1 will be negative t, and x2 will be 0. And so this is what I have for the eigenspace, and this is what I have for the eigenvector, not the null vector or the null space. And then you go to the last lambda is equal to 0 and get the corresponding eigenvector. So now this time, you see our formula is this. But lambda this time is 0. So what I would then have would just be ax. And this is my x. No, this is my a times x. So I needed to say equals 0. What I left out here. From here, I go straight to Gaussian elimination and do my Gaussian elimination up there. Reduce to echelon form. We know how to do that. And what I now have is x1 minus 3x2 plus 2x3 is equals to 0. And I also have x2 minus x3 is 0. And for me, I consider x1 and the x2 are leading variables. x3 is not, and therefore is a free variable. Let x3 be t. And if x3 is t, go to the other side, then x2 will also be t. x2 will also be t. And I can see what x1 would be. x1 would be 3t minus 2t. Because it's x3, no, it's 3x2 minus 2x3 when we take it on the other side. So that it becomes t. So we have t, without t, without t, or we have 1, 1, 1, t. And so when I'm talking of the eigenspace, is what it will be, eigenspace, or it will be this. And what about the null space? I just remove that t. They have the null space. So this is what I have. These are my answers. So I found the eigenvalues and the corresponding eigenvectors or the null spaces. Compute the eigenvalues of A and find the basis for corresponding eigenvalues. I will not read, I'll only mention a few terms. I can see that after this was the characteristic polynomial. And when I tried to solve it, it was giving complex values. In fact, what I have is a negative square root of a negative number. So in fact, that is 2 plus or minus 6i out of 2. Because you know that the square root of 36 is the same negative 36. The square root of negative 36 is the same as the square root of negative 1 and the square root of 36. And the square root of negative 1 is I. And the square root of 36 is 6. Plus or minus. Plus or minus. And so that is why we see this. So that lambda 1 will just be 2 plus 3i. This is 3i, and the other lambda 2 will be 2 minus 3i. So those are the lambdas, and you can proceed with the same knowledge to find the eigenvectors. Do the same thing, and it's very easy. I'm not seeing anything that will be tricky. Anything tricky because you just subtracting. If you have a minus lambda I, but now if lambda is this, lambda is that, you subtract it from 1, subtract from this diagonal, so 1 minus 3i. What do you find with 1 minus 1 plus 3i, which is just 3i. That's why you see 3i. along this diagonal. Along that diagonal, and then after you reach here, the next thing is to use Gaussian inversion. So you want to make this one 0. You want to make this one 0. So how do I make this one 0? I need to multiply this by a value that will give me 3. So if I multiply the entire thing by I, from multiply the entire thing by I would have 3I times I, which is negative 3. So that negative 3 is a product. So what do I have? What I have there as a step? The step is take row 2 minus 3 row 1 multiplied by I. Row 2 minus row 1 multiplied by I. So this one by I will be 3. Negative. Will be negative. So negative 3, this negative 3 minus 3 give me 0. That's what I have. That is 0. And then this one times I will be negative, it will be 3I. So 3I from this 3I again will be 0. I thought that was make down the best one we want to be assisted. To see what I did, because I didn't write the step. So the step I've said is just row 2 minus I multiplied by row 1. That's what I did. Now, so when you reach here, you realize that x2 would be a free variable. So you say let x2 be t. What do we have? 3I x1 plus 3x2 is 0. But if we say let x2 be t, so that means 3I x1 is equals to negative 3 t, or that I x1 is equals to negative t. But you can make x1 the subject, divided by I both sides, divided by I both sides, and find that x1 is negative t out of I. So multiply by the conjugate in the numerator and the denominator. When you do that, you have negative ti out of negative 1. I times I is negative 1. So this will give you positive ti. So that your x1 is ti. X1 is ti and x2 was t. So that x becomes x1, x2. x1 is ti and x2 is t. Or if you want, you can write it as 1i, 1 with a t here. And this one is the Eigenspace, or this one is Eigenspace. So that the null space will be I, 1. This will be the null space or the basis. And the question wanted us to find the basis. So the basis for this lambda here, lambda 1 would then be I1. And that's what I did here. So let me just now show you my work. That's what I got. I got it as a transpose, I1 transpose. Now I do again for this lambda 2, subtract it from A. And when you subtract from A, this is the matrix you get. And then multiply by X, and then use Gaussian elimination. And the question again to assist you is, how did I get a 0 at this point? Let me put the step here. I2 row 2 plus I row 1. So in order, if I multiply this by I times I will be negative. Negative times this negative 3 will be positive. So when I add positive 3 minus 3, I get it. And then this times I will be 3I. Add to this 0. So that's how I got it. That's how I got it 0, 0. Then again, just let's look at this and realize that I have negative 3I x1 and plus 3x2 is equals to 0. So x2 is a free variable, let it be t, so that negative 3I x1 will be negative 3x2, or that I x1 would be t. So that x1 would be t divided by I. And do the same thing we did to get that x1 would be negative t. When you multiply this denominator by I and this numerator by I, and realize that I times I will be negative 1. So that this will be ti divided by negative 1, which gives you negative t. And so that it will now be negative t, negative t, which is negative 1. There's an answer. It was negative tr. Yeah, so then the basis then becomes negative I1. That is the basis for corresponding to the eigenspace of this eigenspace of this eigenvector, eigenvalue. So that's how we get it. I think those examples are enough on determining eigenvalues and the eigenvectors. So what for him, and then you will follow it. So this question, if I find what I wanted just to, what I made me good example was that this eigenvalue was the same. When I solved this, I found that one of the results would be lambda 1 is equal to 2, another one would be lambda 2 is equal to negative 1, and the other one would be lambda 3 is equal to negative 1. So then I wanted to show how to get the eigenvector for these two, which is of course the same thing. So let's just go straight to the eigenvector for these two. Eigenvector for lambda is equal to 2 is easy. Just subtract 2 from the leading diagonal here. Subtract 2. And when you subtract 2, this will be 0, this will be negative 1, this will be negative 5, where it is. Then multiply this x as equal to 0 and use Gaussian. So for me, we discover that x3 would be, x3 then would be what? Would be a free variable, and so equate it to t, and find x2 and x1. So when you do that, this is what you get. And you've done this before. You've solved the systems of the equation. Now, so I have lambda 3 and lambda 1, lambda there, and I see what I get. From the leading diagonal, it's the same as adding, this is a matrix here, into negative 2. The rate that I have here. Multiply by x and equal to 0 and use Gaussian elimination together by this x1, x2, and x3. So that's what I did. So when you use Gaussian elimination, this way you end. At this point, you notice that x3 is a free variable, but the leading variables are x1 and x2. So then you would say that x3 be t. So The last equation here says that x2 minus x3 is 0. So when you make x2 the subject, then you will find that x2 is x3. But x3 is t. So x2 would also be t. That's why you see this. What about x1? So let's just see. Let's come back to this equation. So then 3x1 will be the same as negative x2 plus x3. When I take this to the other side of the equal sign. But what is this? X2 is t, so negative t, and this is t. That means that x1 therefore is 0. That's why you see this. So the eigenvector therefore corresponding to this eigenvalue will be 0, 1, 1. This one has a multiplicity of 2. That means we have got 2 eigenvectors, eigenvalues, and these eigenvalues, 2 eigenvalues have the same eigenvector. So that is the only thing I need to mention on this example. Find the eigenvalues are all distinct. I think it's anything tricky for this question and be able to copy it or compare yours. Compare your work with mine. Okay, let's look at this other example. I want to see if there's something of values on the corresponding eigenvectors and then discover that it's 2 and lambda 3 is 2 eigenvalues, multiplicity 2. So I just want to look at lambda 1 is equal to 2 and see. It will also work for lambda 2 is equal to 2. So once I just solve for one, I'll solve the other automatically. You already know how to do it. Now this minus 2 will be 2, this will be c. A minus 2i x a minus 2i. Then times x is equal to Gaussian elimination. We put this on center to create 0. That means row 1 gives me this. At this point, you notice that only x1, because this one I have 2x1 minus 6x2 plus 2x3 is equal to 0. So you notice that only x1 is a leading variable. Only x1 is a leading variable. The rest are free variables. So let x2 be a, because it's a free variable, and x3 will be, because it's also a free variable. Then that means 2x1 will be the same as 6x2 minus 2x3, which is, but x2 is a, so I'm talking of 6a, and this is b, so I'm talking of 2b, and that equals to x1. So that means x1 therefore divided through by 2 will be 3a minus b. So that is why I write this. So that therefore means that if I wanted the eigenvectors, I would have x1, x2, x3, but I know what x1 is 3a minus b. I know what x2 is. X2 was 10. X2 was 10. And I know what x3 is. X3 was b. Let me say a plus. X2 was b. Let me say 0 plus. to make my work easy. So in fact, this is the same as if I factorize A out, then this is the same as the column of A, this is 0. The column of A would have 3, 1, 0. And the column of B, if I factor B out, would have -1, and would have 0, and would have 1. So that means I had two eigenvalues. One was lambda 1 is equals to 2. Another one was lambda 1, 2 is equals to 2. That means, and I have two eigenvectors. So one would have eigenvector 3, 1, 0. Another one will have eigenvector -1, 0, 1. So I can just say this one has this eigenvector, and this one has this eigenvector, or this. But this is the working. So that's what I did here. That's what I did when I discovered that I would have this. So I then said that lambda is equal to would have two eigenvectors, and one is this and another is that. Then I proceeded now to find the eigenvector lambda 3 is equal to 0. And that one you can do. Let's look at diagonalization of matrices. I'll straight away begin with examples, and just before that, if I'm given matrix A, then the diagonal matrix to A will be given by P inverse AP, where P is the matrix formed by whose columns are the eigenvectors of A. So P will be a matrix whose columns are the eigenvectors, and this P inverse is its inverse. Now, so we'll try to first of all look at how to find diagonal matrices and use that to get a matrix A raised to value n. And so, before looking at matrix A raised to value n, I know that this matrix A can be written as P D P inverse. So that is, after getting the diagonal matrix, I can express this in terms of the diagonal matrix by multiplying P times this diagonal matrix times the inverse of P. That will give me A. That means if I have A square, if I want to square matrix A, then I only need, this is A. So I need to multiply it twice. D P inverse. Then again P D P inverse. And you realize that this is P times its inverse, which is identity. So that now A square will be given by P D square P inverse. In other words, if I'm given A raised to n, I can write this as P D raised to n and then P inverse. So these are very important knowledge that I'll be using to get a square of a matrix, and again, I can use the same knowledge to get the square root of a matrix, or even the cube root, or even the fourth root of a matrix, so long as that matrix is a positive matrix. So when I talk about positive matrix, I mean a matrix whose eigenvalues are positive. That is a positive matrix. So if it is a positive matrix, then you can get the square root of that matrix. Because you can get a square root of any positive number, or a number that is 0. Like 9 is positive, so it's square root. Okay, -9, that one would be complex, a complex number. So I'm just talking about a positive matrix that I can get. If I get positive eigenvalues then it means that matrix is positive, and therefore I can get it squared using this knowledge. So that the square root of matrix A will be given by P, the square root of D, P inverse. So all these are covered in the following examples. The first example, diagonalize this matrix and use it to find a raised to 5. So the first thing I do is to get the characteristic polynomial and then equate it to 0 and get the eigenvalues. So it begins from here. And the characteristic polynomial for this, you know how to get it. It will be lambda square minus lambda, the trace of A, plus the determinant of A. And so lambda, that will be lambda square, the trace of A is 6 times lambda, the determinant of this is -7. 6, 5 minus 12. So when you put this to 0 and solve for lambda, you get that lambda will be -1, lambda will be -7. So lambda 1 will be -1, lambda 2 will be -7. Now we know how to get the corresponding eigenvectors, and I've already shown that in previous video. So the eigenvector corresponding to this eigenvalue is that, and the eigenvector corresponding to this eigenvalue is this. Now, so all I needed to do was to get the eigenvectors. So I have the eigenvectors, and as I said at the beginning, when I arrange those ones in column of matrix, I form matrix P. So matrix P is just a matrix whose columns are P. And the second, the inverse matrix. What is the diagonal matrix? The diagonal matrix will be given by P inverse AP. This is P inverse. And the one that follows is M. And then you have P. This is M. And this is P. So P inverse AP. When you multiply that, you get this. So this might be. What you notice is that these were the eigenvalues. This was the eigenvalue corresponding to the first eigenvector here in P, and this was the eigenvalue corresponding to the second eigenvector. So what that therefore means is that if my P would have been, if I would have begun with this to form P, and then followed by that, that is 2. That is 2. If this would have been P, I would have proceeded to get its corresponding P inverse. But then D would have been, this is an eigenvector corresponding to lambda 7. So I would have had 7 there, and this is eigenvector corresponding to lambda is -1. So this is -1, and this is the same. So this is how D will have been. So that therefore means how you arrange your vectors in P determines your D, your diagonal matrix. So that is the only important thing. So the question was find D and then find a raised to 5. We use this from N P inverse. And what I want to raise from 0.05. And then we also raise any more 5. So it's very easy getting matrix raised to R. Now let me look at this. Find P such that find the square root is, find F of. So then that is to find the characteristics founding eigenvectors. You know how to get it. I've factorized 1 is 8, and lambda 2 to get the eigenvector corresponding to lambda. And then the 8 is a possible true. lambda 2 is equals to, I've found it to be negative 1, 2. I found it to be negative 1, 2. So I have this eigenvector and this eigenvector. I arrange them to form P. So I began with which one? Which one did I begin? Where's P? Yeah, my P is here. So I arrange them. I began with this, then this one comes. So that is P. Then from, if you have P, you now to get the inverse of the matrix. So that means get P inverse. So that D is P, and you multiply them in that order. You don't need a change because matrices are not commuted. So you multiply them in this order. You multiply the first matrix by the second matrix. The answer that you get multiplied by the third matrix. It expected that here was corresponding to here. That was our expectation. And then to lambda is equals to 2 lambda matrix. And you know what will have happened when we begin with this here, 8 to the H. So what was the other question? The other question was to find RS2. Was it RS2 4? And using our formula, RS2 4 would be P, D raised to this is our D. Our D, and this is the P. 2 raised to 4 is 16. You get as RS2 4. This is the formula. So that just means the leading diagonal of this. And then multiply with this. So at this point, I can see which got. So now I factor it out, this is what I got. And then finally, given f of, I've been given the question was that, yes, f of t was t cubed minus 40 squared plus 5. Yes. And my d was what? This was my d. My d was 8002. So what I only need to get, what I know is that f of a will be given by p f of d, p inverse. But f of d, if you get f of d, just get f of 8. And then we get f of 2. So f of 8, where t is with 8, 8 cubed, minus 4, 8 squared, plus 5, 8, minus 6. This gives you f of 8. And then f of 2, just where t is, put 2, that will be 2 cubed, minus 4t squared, plus 5t, no 2, minus 6, that gives you f of 2. So let me just now go straight to what I did, how I got, what was my result. But you can use your calculator to see what you get. I've done that using my calculator. And so what I find f of 8 to be. F of 8 I found to 19.84. That means in the diagonal matrix, where there was 8, I have f of d, where there was 8, it's 290, and where there was 2 is 84. And then becomes, this is my error, then the result becomes that. Example on the diagonalization of matrices, you can get question alone. Find errors of 6. The eigenvalues, you'll find the eigenvalue 1 and 4. I've to show an example once now the same way it works. Now, bringing to lambda wise, and the one corresponding lambda has to form P. I've arranged them here, arranged them there to form P. Then use your knowledge of matrix inversion to get the inverse of P. So I did. What is D? P inverse of it. Then matrix like matrices. That's not as expected. Moving to the first agent, the eigenvalue corresponds, and 0 was the last eigenvalue corresponding to 1. So its corresponding eigenvalue, which is 0, lambda 3, is 1. So this is P. Okay, we're there. Okay. I had shown this P, then I ask the inverse, and we come up with its eigenvector and so on. Now, from there, I can get, and it will be P d raised to 6 just raising the a, and that's how we do that. For the last example, then is see the eigenvalue 2 are the same size. Now, the eigenvectors are this, and that is the only point on this one is to form P, find the D. That's how we look at many examples. You can always post this to the eigenvectors to go back to very fast so to get the inverse of matrix. Doing that matrix only after you have the eigenvector, then you get D, and you know the formula first a raised to n, only D, then inverse. Thank you for watching.